Welcome to another AP Physics 1 practice problem session where I'm just going to do another AP Physics 1 problem. Now, this problem is very unique because this is actually an experimental design problem. And those problems are one of the most important problems you have to know and have to do well on the AP exam. It's for you to solidly consider yourself a 5. If you don't do quite well on the experimental design, your odds of getting a 5 will be jeopardized. But in that case, let's take a look at what this problem brings us today. Well, first of all, I notice that we have a stand, and we're given a bunch of cylinders, and we're actually given a string. Sorry, a spring. Well, this is making us very reminiscent of the lab that we did a while back on a vertical spring. So this problem will probably be about simple harmonic motion. So if we look down, we notice that it's asking us to find the spring constant K of a spring. Well, that probably means that we're going to deal something with, well, simple harmonic motion because springs are usually associated with that. And if we go down even further, we realize that, well, we have a sinusoidal graph, and the force is changing with respect to time, and the velocity is also changing with respect to time. So, as a result, this is probably a simple harmonic motion problem. Okay, so with that out of the way, let's actually start dealing ourselves with questions that we could start first. Now, this was in the 2024 AP Physics exam, so actually, this was the exam that I wrote. Now, when I wrote this exam, I will be honest here, I wasn't able to do question A nor B at the first hand. Now, looking back at this was complete stupidity. There was no reason why I couldn't do part A and B, but I wasn't able to think of a solution then. So what I did was do part C. After I was finished part C, I finished the rest of the exam, and then I came back and I was able to get part A and part B correctly. I didn't spend too much time realizing that I couldn't think of a possible solution to this problem because I knew that if I had enough time to come back, I'd probably be able to find a way to actually do part A and part B. But anyways, you should be able to do part A and part B. So we're going to start with part A and part B first. The first thing we should notice is that they actually already give us the equipment for the measurement. They give us the stopwatch and the digital scale. That will yield us two quantities, mass m and the period t, or whatever time that you're trying to measure. And we do recall this equation that t is equal to 2 pi, this is given on your formula sheet, m over k. So if we could exploit this formula, we could effectively find k over here. And that's really easy to do. All we need to do is square both sides, so we get that t squared is equal to 4 pi squared m over k. And then with a simple cross multiplication, we get that k is equal to 4 pi squared m over t squared. Okay, so that was one part of it, and we've already derived our expression here. But first of all, we do have to define our symbols that we used here. So we're going to measure the mass of a cylinder. So let me actually use the text function. Mass of the cylinder. And over here, we're going to measure period of oscillation. And when you have these two quantities, you're basically set for the problem. We just need to simply tell the AP exam reader what the quantities are. So let's use, to be consistent, M and big T for period. And now all we really need to do is describe a procedure. Now, before we actually jump into this, we have to make sure that we don't actually use point form for this, because point form isn't good for the AP exam. In fact, they won't even mark it if an entire problem is written in point form. So, we should realize that the problem is asking us to provide enough detail so another student can replicate the experiment. So we have to explicitly which equipment we use to measure, and also any steps to reduce the experimental uncertainty. Now remember, here's a very, very common trap that we have. Uncertainty does not mean is not more trials. Doing more trials doesn't mean, reducing uncertainty doesn't mean doing more trials. This is a key misconception that is held. That is simply increasing your precision. To reduce uncertainty or to increase the certainty, you need to alter your parameters. What are your parameters? Our parameters are the time of oscillation and the mass of a cylinder. Well, we can't really change the period of oscillation that directly, because if you recall, even if you stretch a spring further, amplitude is not correlated to the period of oscillation, so we can't directly change a period of oscillation. However, we are given multiple cylinders, so we can change the mass of a cylinder to fit our needs. Okay, so let's start by, first of all, telling the reader how we can measure these quantities. First of all, use the scale to measure the mass of a cylinder. After attaching the cylinder to the spring, displace the spring by a small but noticeable displacement from the let's say the equilibrium point. And to be more careful here, we should actually let the spring reach equilibrium first. We should say let the spring cylinder system reach equilibrium. Then displace the spring, blah blah blah, and measure, let's say, how long it takes for the spring to complete a full oscillation. Let's say complete 10 full oscillations, so we would be increasing our precision as well. And divide by 10 for that result to get the true period. Repeat this exact procedure with different masses and average the periods. Then plug in, or we should say finally, plug in the known values for period and mass to yield a straight line for the spring constant. All right, so this would be our procedure over here, and we would be pretty much done. Okay, now part B is actually where I jumped ahead a bit. Now it's asking us to how we could use the quantities that we're given here and something else to measure the spring constant K of a spring. Well, this is actually quite simple. We just need 4 pi squared m, and the horizontal axis will be t squared. So we would write 4 pi squared m t squared. Now, in fact, you don't actually need to write 4 pi, because what you could do is you could address this 4 pi squared constant in part II. So all we need to do here for II, since we wrote our answer for B, we just need to say, take the slope of the graph indicated above, and the spring constant will be the slope. And you, for safety's sake, you might say rise over run. But you probably have to explain a bit more than just write rise over run. But this is enough if you're kind of running out of time or you think you still have time to come back to this later. All right, so that was part B. That was quite easy. Let's move on to part C now. So part C, we notice that we are given two graphs, and based on these graphs, we have to calculate certain properties from them. So based on our data from the velocity time graph, we have to calculate the change in kinetic energy of the cart from time 0.5 to time 2. Okay, well, that's going to be a bit interesting. Well, we have to find the kinetic energy from 0.5 to 2.0. Okay. Well, we know that our kinetic energy expression is equal to 1 half mv squared. Well, if we have that, the change in kinetic energy from 0.5 to 2 is equal to the kinetic energy at 2 seconds minus the kinetic energy at 1 second. Sorry, at 0.5 seconds. All right. So looking at the graph, K2 will be 0 because at that point there is no velocity for the spring oscillating left to right. But at 0.5 seconds, we realize that it's reached a maximum. So that would be 1 half multiplied by 0.3 squared. And we would get that, well, basically this would be 0.9 divided by 2. And if we multiplied by, let's say, 100 on each side, we would get 9 over 200. Now, if you had a calculator, you would plug this in, but I don't have a calculator on me right now, so this is good enough. And don't forget your units. We should write joules because we were talking about the change in kinetic energy. Now, I know you might be a bit confused because I've neglected the minus sign here, but we're just looking at the change in kinetic energy here. So it depends on the context, but if you want to be safe, and probably I would be too, I would add the negative signs in front. Alternatively, I'd write the magnitude and I'd explain what I mean I'd explain my line of reasoning from, well, of why I don't have a negative sign, and I explain that it's because it's this magnitude and I've lost that amount of energy. Okay, for part 2, we have to take a look at the estimated change in momentum of a cart from 0.5 to 2.5. So from here all the way to here. Okay, well, that's a tough nut to crack. Well, we have to realize that momentum is equal to your force is equal to your change in momentum with respect to time. And that is given on your formula sheet, I believe. And since we know that the force is equal to the change in momentum over time, we can estimate roughly what the momentum is at every point in time. Now, you would be slightly mistaken to assume you could just say delta P is equal to F delta T. But realize that, well, if you take the average here, then you're getting the average change in momentum. Now, of course, that's not going to do anything, but we're looking at the change in momentum of a cart instantaneously. All right, so what we actually have to do is do a funny little trick here. We have to take the tangent lines on each slope. And what we realize is after we take the tangent line, these two slopes will actually, we could find their slopes, and all we really need to do is find their differences. But do we actually need to do that? Well, no. The slopes are approximately the same, so they're all pointing down. So if you simply minus these two same quantities in the same direction, you're going to have 0. So we don't actually need to have to write any of this at the start. All we really need to do is say 0, because it's not asking us to derive anything. And we simply need to write the instantaneous momentum of the object is the tangent line of a FT diagram. We note that at both times the tangent line is pointing as steep and in the same direction. Hence, the instantaneous momentum of the objects is unchanged, so the change in momentum is 0. All right, so short and sweet, and we get straight to the point. So no need to do actual calculus on this problem. That'd be very unnecessary, but it's cool to have this understanding of tangent lines, or else you might have to explain this problem a bit more, which is a bit more complicated. Okay, number 3, does the data from velocity time graph confirm your estimation from part CII? Okay, well, from time t is equal to 0.5 to time t is equal to 2.5, we get that the velocity is, well, at a maximum 0.3 at both times. Well, if your velocity isn't changing at these both times, there's no reason, since momentum is just mv, there's no reason for your momentum to be altered. So what you could write is this. Yes, the graphs confirm my estimation. The velocity of the objects are the same at both times. Since p is equal to mv, this also means that the momentum is unchanged, and we reach the same conclusion aforementioned. All right, so that is our answer for part 3, and the same piece of advice that I've been saying since the very start. Whenever you have these questions where they're asking you to confirm your own estimations, not someone else's, not a student, but your own estimation in a previous part, your answer is almost always, and I could say almost always as always, yes, because they're asking you to check your work. So if your answer doesn't match up, then you made a mistake somewhere and you have to check your work again, unless if you're running out of time. If you're running out of time, leave it there. You'll earn consistency points, but do know that you will lose a points where you didn't get the question right. But other than that, this question was a very standard lab question that I hope that the previous labs that we've done will be able to stimulate you to breeze through this problem. And other than that, I hope to catch you on the next one. See you soon.